Hi everyone, welcome to another fun-filled edition of Fluid Earth Dynamics. And I'm kind of jumping in here, horning in on David's segment to present a few ideas about flow of a laminar fluid down an inclined plane. So this is going to be a Newtonian fluid. And basically what we're going to do is build on some of the ideas that David has been presenting and developing with you and apply them to gravity-driven flow down a plane. And you'll see the same concepts appearing but in slightly different form, and hopefully it's useful in itself, but hopefully it'll also help you solidify them a bit by seeing them in a new context. So off we go. So we're going to analyze the momentum balance in a unit slice of the flow. So you can see that right here, and you can imagine it as a little thin vertical segment of the flow of unit width in which we're going to find the momentum balance, and eventually we're going to find the velocity profile, and we're going to try to find out how much fluid is flowing down that unit slice there. Okay, so we'll move on. So to get into the momentum balance, let's remind ourselves about the stresses that we've been talking about. Again, the core idea in fluid flow is that we're relating velocity gradients to shear stresses. We're driving flows with things like pressure, which is our normal stress. Today we're not going to be using pressure, actually. We're going to be just using gravity to drive the flow, but we do have still a stress to think about, and that is the shear stress. So just as a quick reminder, in the top left here I have a couple of shear stresses shown. Here's a shearing motion shown, and then down here another shearing motion. So the one down in the bottom left is the one that we're interested in for the flow today, where we're looking at velocity shear and trying to relate that to the shear stress. So get rid of that notation and off we go. Okay, so the first thing we want to think about is the momentum balance. And even though I said before that we were going to do this for a laminar flow of a Newtonian fluid, actually the momentum balance that we're going to develop applies to anything sliding down an inclined plane. That could be an ice cube sliding down an inclined plane in your kitchen, or it could be the flow of some very complicated material. But the momentum balance is actually quite simple, and it's a balance between friction forces in the fluid, which will materialize as shear stress, and the gravity force pulling the fluid down the plane. So to analyze this momentum balance, we just need to look at the force balance on a block of fluid. So I've outlined it here in this dashed box. And the force in question is gravity. And of course, the gravitational force acts straight down. So it's on our vertical coordinate. And in order for that gravity force to have any effect in moving the fluid down in a particular direction, there has to be a slope to the surface. And the way we incorporate the effect of that slope is to resolve our gravity force, downward force vector, into two components. One that acts normal to the bed and that we're going to ignore for our purposes here, and then another one over here that acts parallel to the bed. And the basic force balance is pretty simple in the sense that the shear stress just has to counteract that component of the gravity force. And that's the way it works as long as the flow is in steady motion. So it's not accelerating, therefore there are no, the sum of the forces acting on it is zero. And in this case, we've said these are the only two forces, so they have to balance one another. So we are looking at a balance between the downslope component of gravity and the bed shear stress. So, and for the moment, we have assumed that the force balance we're looking at takes place over the whole box that I drew, and maybe it'll help if I clear that out so you can see it a little bit better. So it's this box here outlined in the dashes. So we're just doing a force balance on that box. Now, let me clear that out. The gravity force then is just the weight of the material. So that's easy to work out. It's the density times the volume of the box. But then we want to take the component of that down slope And so we have to resolve, as I said before, the weight force into its two components. With a little bit of trig, you can see that the component that we want is the small component, and that's the sine. When the angle is small, the sine is the small component. We are going to take a little bit of a shortcut and say that because the typical slopes that fluids we're interested in flow on are quite small, the sine and the tangent and actually the angle itself expressed in radians are all the same. So we're going to replace the sine with the tangent, and the tangent of the slope angle is typically what we refer to as the slope. So that's capital S in this diagram, and you can see it right here. So that's the slope. It's the tangent of the slope angle. And this slope is typically expressed in dimensionless units. If you remember driving on highways with steep slopes, you might have seen signs with things like a gradient of 6%. That means it falls 6 units in the vertical for every 100 units that you go horizontally. That's a typical expression of slope, and that's essentially the one that we're using here. So off we go. So this gives us an expression for our bed shear stress. The shear stress, which we've written as tau naught up here, is just the weight of material per unit area in our box, rho GH, and then times the slope to give you the downslope component associated with gravity. So simple enough. This is a pretty simple force balance, and again, you're going to get sick of hearing me say this, but I'm going to say it one more time, that so far we have not used the fact that we're dealing with a fluid. This is just a simple momentum balance, and it applies to any material, no matter how complex, as long as it is in steady motion down an inclined plane and no other forces are acting. Okay. So you guys should think about the questions that I've posed here in this self-quiz. I won't go through them all, but I want you to just ask yourselves, given the formula that we just derived, what happens if we do these various changes? And the answers are at the end of the slide set for today. So onward and upward. Okay. So we now have an expression for the shear stress at the bed, but we need we'd like to have an expression for the shear stress throughout the entire fluid, because that's what we need to get our velocity profile and ultimately work out the bulk flow rate and other interesting things like that. So we need to know the shear stress elsewhere in the flow. So I've simply rewritten our expression that we derived here, but I left the 0 off the tau. So now we're going to try to think about shear stress anywhere in the fluid. And if you did the self-test and if you understood what happens as we change the depth, you'll realize that if we make the depth smaller, the shear stress is going to be smaller. So in particular, for example, if we reduce the depth by a factor of 2, we'd have to reduce the shear stress by a factor of 2. So I just gave you one of the answers away, but we can live with that. Okay, so we'll get rid of that and onward and upward. So suppose we now consider some elevation higher in the flow and ask what the shear stress is at that elevation. Well, we already have done that, because if you're above the bed, the depth has been reduced by the distance that you moved up away from the bed, and so the shear stress is just given by that same momentum balance, except that the depth is replaced by the depth of fluid above you at the elevation where you are. So in particular, if we just pick some elevation here, we'll call it H prime, so that's H prime there. So we have H prime distance of water above us, and if we started out at the bed, at the point at which we have H prime distance above us, we must have Y distance below us, because the sum of Y and H prime has to be equal to the total depth. So we moved up in the flow a distance Y, and whoops, I went a little bit over there, and at that point we have some shorter distance H prime still over our head. That's the weight of fluid that we have to balance with our shear stress. And so the shear stress as a function of height is just given by this new expression that looks alarmingly like our old expression, except that the depth has been replaced by a smaller depth, which is H prime, and as I note down here, that's just equal to the total depth minus the elevation where we are. So really simple, and one implication of this is that when we get to the top of the flow, shear stress goes to 0, because there's no fluid over our head at all at that point. And as long as no wind or something is blowing on the top of the fluid and applying a shear stress to it, the stress should go to 0 there. So let's zap that stuff, and off we go. Okay, So the shear stress profile then looks extremely simple. It's linear. It starts at the bed at tau 0 down here, and it decreases in a smooth straight line to a 0 value at the top of the flow h. And the reason for that is given by the explanation that I just gave. So as long as there's no shear stress acting on the top surface, like a wind is blowing on it or something like that, this stress profile, starting at tau naught at the bottom and decreasing linearly to 0 at the top, is the one that applies. So, okay. So now we know the shear stress profile, and we're in pretty good shape, but now we want to know the velocity profile, because shear stress profiles are fine in and of themselves, but they don't really tell us how fast anything is going or how the velocity might change with height. So our job now is to translate that shear stress profile into a velocity profile, and at this point we're doing the same basic logic that you've done with David several times, I think, already, and that is converting a stress profile into a velocity profile. And the question is, what do we know about the relation between velocity and shear stress that might help us to do that? Now, again, let me reiterate, so far everything that we've done applies to any material as long as it's in steady motion under gravity on an inclined plane. But to actually get from shear stress to velocity, so we got a shear stress profile that's vanilla, generic, applies to all kinds of complicated materials. To actually convert that to velocity, though, we have to specify the relation between velocity and shear stress, or velocity gradient and shear stress, and to do that we have to specify a particular rheology. So now we are moving into a specific type of fluid, and of course, as I said at the beginning, that fluid is going to be a laminar flow of Newtonian material. So, off to the races. Well, we know something, because David has taught this to you and shown you examples of it, about how velocity and shear stress are related. We're going to use Newton's stress law, which we can get away with because it's a laminar flow and it's a Newtonian material, and that gives us this extremely simple and useful relation between the velocity gradient, so the rate at which the velocity is changing with height, and the viscosity, which you've learned about, and the shear stress. So we have an equation that links something we know, which is the stress as a function of height, to something we would like to know, which is the velocity as a function of height. So we'll clear that out and move ahead. So we have our stress law. Okay, so, excuse me, I went too far. So with this stress law, we basically have, what I'm going to do is describe in words how this works, and then we'll do the math afterwards. So we know the stress at each height, and we know how the stress relates to the velocity, but we only know the relation between the stress and the gradient of velocity. So essentially this notion allows us to draw a picture that looks kind of like this. We can, for each stress, so I'm going to just pick a stress somewhere in the middle here, I can say, okay, I know what the gradient of velocity associated with that stress is, because I can calculate it directly from Newton's stress law. So for each value of stress, I can put a little gradient in. And the gradient of velocity is just a sloping line relating, in the graph between u, which is up here, and y, which is over here. Now, the way this works, I have u at the top, y like this. So the gradient looks like this. If u is changing very rapidly with y, then the gradient, then we have a big change in u for a given change in y. And where would we have a large change in u with y? Well, it would be near the bed where the stress is very high. So we know that our gradient should look kind of like this. Big change in u, little change in y. And we know that up here the stress goes to 0, so that means that u doesn't change with y at all, and a gradient of that kind looks like this. So we kind of, just intuitively using this formula without doing any math, we can rough out what the stress profile must look like. What the velocity profile must look like. So we'll clear that stuff out and go to the next slide. And so we have a picture of a curved velocity profile. And again, I promise we will do the math in a minute. The other piece that we need, though, is an anchor, because all we know about is gradients. And I can draw an infinite family of lines with the same gradient profile, like you see here, that would all satisfy that relation between stress and velocity gradient. So all these lines that I've drawn here, So all these lines work equally well in terms of what we know so far. So we can't fully solve the problem of the velocity profile until we have an anchor point, one point where we know the velocity at a given height that lets us pick which one of these various profiles is the right one. And of course, there are infinitely many, but I only drew 3. So, well, we do actually know something about the velocity and how it varies with height. And we know, in particular, there's one place where we always know the velocity in at least an ordinary type of fluid, like a Newtonian fluid, and that is at the boundary. So we're going to use that fact as well. So off we go. So we know that the velocity at the bed down here is 0. So right there we know that the velocity is 0, interestingly where the stress is at its maximum. And so we know that the only velocity profile that's right is the one that intersects that boundary. So that lets us pick from all the ones that there could have been the right one that goes to 0 at the bed. Okay, so that's the that was a verbal explanation of the essence of the math that we're going to do. So here's the math. So we start with our stress profile right there. We worked that out from momentum balance earlier. We then, well, I started by rewriting it slightly just to make it a little bit easier to use. I pulled H out. You can see that here. I pulled H out, and that let me write it in terms of the shear stress at the bed, which is a handy thing to do. Then I relate the shear stress to the velocity gradient using Newton's law. I now have a simple equation with du dy on one side, y over here. It's a nice, easy equation, and I can just integrate it once, as David has done several times with you, to convert du dy into u of y, which is what we want. So this is our relation. We just have to do a pretty simple integral, and we are done. So continuing the math, here is the equation that we derived on the last slide. That's the integral. The shear stress at the bottom, tau naught, and the viscosity are constants, so we can take them out. Then you're left with an integral that you learned how to do in Calculus 1. The 1 goes to integrates to a y. The y over h integrates to y squared over 2h. And we have a constant. This constant represents the unknown anchor point that I mentioned last time that we have to specify, or we have to set by specifying the velocity at some height. And we know that u of 0 is 0. That's the no-slip condition. So the constant in this case turns out to be 0 because this piece evaluates to 0 at y equals 0. And so now we are left with what we wanted, which is a velocity profile. And it's not a terribly hard one. You can see that it has two pieces. It has a linear part in y, and then it has a quadratic part, that is in y squared. And the quadratic part is what gives the profile its curvature. It gives it kind of this belly, if you like, shape like that. And so we're kind of done. Well, are we really done, though? It's always a good idea to check your math, to go back and make sure that the thing you derived is consistent with your starting point. So here's our velocity profile that we derived. An easy way to check it is just to differentiate it once so that we have an expression in du dy and make sure that du dy evaluates out to what we think it should at points where we know it. Well, by inspection we can see that at y equals h, we get 1 minus 1, so du dy evaluates to 0, so we get a 0 gradient there, as we expected. And if we go down to the bed, we can see that du dy evaluates out to, in that case, the bed is y equals 0, so we get du dy equals tau naught over mu, the viscosity, so that's that. And I want you to just do a little bit of algebra and convince yourselves that that is the expected expression for the relation of the bed shear stress, tau naught, and the velocity gradient at the bed. And it's, again, I stress this, it's fairly obvious, but I want to reiterate this because I know that this is a mistake people make. Don't mix up the fact that the velocity goes to 0 at the boundary with the velocity gradient. The gradient is actually very large at the boundary. It's the velocity itself that goes to 0. So, okay, enough with all the red marks. Off we go. So I'm going to finish up with something that you've done with David. I'm going to be a little bit more compulsive about it and just find out the average velocity, and with that we're going to find out the total flux of fluid, that is the total integrated flow over this vertical slice. So suppose, of course nobody in this class would actually answer to this description, but suppose we were extremely lazy and we decided we wanted the average velocity but we didn't want to work very hard. So we say, well, I know the velocity at each height. I'm just going to calculate the velocity at 2 heights, let's say. And I'm going to just average those 2 values, and yeah, it won't be exactly right, but that'll be a good enough average velocity. So I pick a couple of heights, and they're shown here. So here's one, and here's the other. I calculate the velocity at those 2 values, y1 and y2, and then I just do a conventional average. I sum them, and I divide by 2. So that is the average over here. And this is how you learned how to do averages in elementary school, right? You just add up a bunch of numbers, and then you divide by the number of numbers that you had, and that number is the average. So that's the average velocity according to this exceedingly lazy method. So, a few minutes later, you drink some coffee, you wake up a little bit, and you're feeling not quite so lazy, and you think, well, I actually do know the velocity at every height. So, I could do a little bit better. Oh, I'm sorry, I've actually skipped a step. We're going to get to the part where we feel guilty and do more velocities in a second. But if we do the average the way I said, with just two velocities, what we're doing in effect is imagining that we can break the flow the way I've drawn here. So we've got 2 segments of flow shown in gray, one in which this velocity here is representative, and another one, a lower one, in which we imagine that this lower velocity is representative. And each one of these segments, we say, is represented by that velocity. And we can picture what we've done as dividing the flow into these 2 segments that we represented with their average velocities. And if we think about it this way, we can replace the n, the number of velocities that we averaged, with the total height of the flow, so that's given here, the depth, divided by the thickness, or the height of these 2 segments. So the height is delta y for each segment. I've divided the flow into 2 segments in this case. So h, the total height, divided by delta y, the height of each segment, is obviously 2. So this little piece here is a slightly more sophisticated way of writing our 1 over n that we learned to do when we averaged in elementary school. So, okay, onward and upward. But as advertised, we had some coffee and we felt guilty about only using 2, so maybe we decided, okay, we'll do 4 velocities and get a slightly better number. And you can see that here. Now I've done 4 velocities, and you can see I've got 4 little segments, 1, 2, 3, 4, and each one of those is delta y high. And of course, now we've divided our same total height into 4, so delta y is smaller. But the delta y over h still represents 1 over n, the averaging. Whoops, I don't know why I can't write. There we go. The number that we use to normalize the average from elementary school onwards. And we realize, well, 4 is probably going to give us a better answer than 2. Then we have a little more coffee, and we figure, well, there's really no reason at all not to just use them all. So if we pass from this sum here to the integral by making delta y go to infinitesimally small, we just take this little delta y, we swap him inside, we swap him to the right, and we replace our sum here with an integral, and lo and behold, this is calculus 1, and you've gone from a sum to an integral, and we represent the average velocity by an integral of velocity over height. So there's the velocity as a function of height, there's the height itself. We sum it over the whole height, that's 0 to h. We divide by h. This division is the leftover of the fact that we have to normalize by the number of measurements we took, or the number of numbers in our average, and we get the average velocity out. And you can see that each piece of this equation, the integral down here, is represented by a piece up here in our sum, which came directly from the elementary school version of averaging. So that's how you average a continuous function, and we've used it in the course, and we're going to use it again and again, so it's worth learning how to do. And by the way, this approach works for averaging any continuous function, and you can even do it in more dimensions if you want, and it's a pretty straightforward generalization. So, okay. Onward. Just, as I said, this is how you find the average of a continuous function, and David has done this with you too. Once you've done this much work, you get a freebie, which is, if you know the average velocity, you also immediately can find the so-called unit discharge, which is the bulk flow rate. So all the flow through this vertical slice, summed up, is given by this little lowercase q. And by the way, I have to warn you that this lowercase q is used for other things too, so this is one of these symbols that unfortunately gets used in more than one way in the world, and unfortunately you have to get used to it. But little lowercase q is just equal to the integral without the 1 over h normalization. So off we go. And oops, I forgot to mention that the other, if you compare this equation and this equation, it's pretty clear that q is equal to the average velocity times h. And that's a relation that David has also used in the course. So, and we will use that quite a bit down the line. Okay. So now we're just going to do the math and substitute in. We have our velocity profile. So we said that the way to find the average velocity was to integrate the velocity over the whole domain, over the whole depth, and then divide by that depth, so that's there. I've just put the velocity in here and integrated it. So this is the velocity profile that we derived earlier. The y integrates up to y squared over 2. The y squared over 2 integrates up to y cubed over 6, and there's our h hiding out in there. We evaluate this at 0 and h. 0 evaluates to 0. H gives you an h squared over 2, an h cubed over 6h, which is h squared over 6. Subtract a sixth from a half, and you have a third, and that gives you this handy thing, which is the average velocity in terms of the shear stress at the bed, tau 0, the height of the flow, the depth of the flow, and the viscosity down here, and then a handy 3, which is just thrown in for good measure. No, that's what you get by subtracting a sixth from a half. So that's our average velocity. Multiply that by h, and you have the little q, the flux per unit width. And that's all pretty useful. So this is a summary of what we've covered. And this is kind of a self-test in the sense that you should be able to reproduce these on your own. Use the slides at first, but then try to make sure you can do them on your own. Find the shear stress profile for any material, so this is whatever material, as long as it's moving steadily under gravity down an inclined plane. That's the first thing we did. You should then be able to recognize that to convert that to a velocity profile, you have to specify the type of fluid. So the stress profile is generic, the velocity profile is idiosyncratic. It depends on the material. So for a Newtonian fluid in laminar flow, we found a velocity profile associated with that shear stress profile. And then the third thing we did was to average the velocity profile by integrating it, and that gave us as a freebie an expression for little q, the total bulk flow in a unit slice of flowing fluid, which we're going to have cause to use a number of times later in the course. So there are answers to questions in a slide or two, but that's all I have for today, and enjoy. Bye-bye.